to be here. It's really a pleasure, and I'm very excited to give these lectures. So initially I was given 6 hours of lectures, but then Pasquale suggested that I give an additional 2 hours just to introduce some of the technical stuff that will be used next week. So this is what's happening today. So today is just it's not really the first lecture, it's just some sort of technical, let's say technical preliminary. And I will introduce the 2D free boson conformal field theory. And this is the basic field theory that underlies the Luttinger liquid, so it should be useful to follow not only my lecture next week, but also the lecture by Thierry Germarchi. Okay, so I will instead of calling things the free boson CFT, I will call it Gaussian free field, because this is somehow this has become the standard terminology nowadays in mathematics, and so I think we should get used to it. But it's really the same thing. So I will say Gaussian free field, or GFF, and it means do what? Yes, like that. Yeah. All right. So. Yes, so free boson CFT or GFF, it's really the same thing, but GFF has become the standard name, and so I'm going to use that. All right, so let's start. So first I will define this object, and so we are going to start with Gaussian probability distributions. So so you all know that this integral, so the Gaussian integral, is finite for any gamma, real number gamma that is positive. And this allows to define expectation values taken with respect to that measure. So we can, for any function f, we can define the expectation value of f of h as this ratio here. Okay, and this defines a Gaussian probability distribution. Now, in particular, we can take f as an exponential and calculate the expectation value of e to the ah, and this turns out to be equal to e to the 1/2 of a squared gamma. And by expanding in powers of a on both sides, you can check that this gives hn equals 0 if n is odd, and some combinatorial factor, factorial n over 2 to the n over 2, n over 2 factorial, if n is even. If n is even. I forgot to say that I prepared some lecture notes which you can find on the website. So you don't necessarily have to take notes. Everything is typed in LaTeX. All right, and so this combinatorial factor and gamma to the n over 2 here. So this combinatorial factor has some nice interpretation, which is that if you just write h to the n as a bunch of h's like this, n of them, then you can just write this correlation function as this. So you can just write separately all the different possible pairings of those h's. So here, like this. And so on. So And this combinatorial factor here is precisely the number of pairings that you can write. And the rule then is that each pairing here gets replaced. So if each pair gets replaced by the expectation value of h squared, which is gamma. Okay, and so this is the same thing as this, and this is basically a baby version of Vix theorem. All right, and now so everything goes through for higher dimensional variables. So if you replace h, which was just a real number so far, by some vector, n-dimensional vector with n components, and you replace gamma by some n times n matrix. So then you can define again expectation values of some functions of a vector h now as an n-dimensional integral e to the minus h transpose gamma minus 1 h divided by 2 f of h divided by this. In particular, you can take expectation values. So if you have now some n-dimensional vector A, and you calculate that expectation value, you will find that it is 1/2 of a t gamma A, which is the generalization of this. And again, by expanding in powers of A on both sides, you will find the Vix theorem for this more general n-dimensional distribution in the following form. So this will again be equal to all the possible pairings. And the rule now is that each time I pair up two h's, I have to replace them by the 2-point function. So those are components now. So I have some indices here, I1, I2 to IN, and so the pair here gets replaced by the matrix element IJ of the matrix gamma. Okay, so these are Gaussian probability distributions. And then let me go here. Yeah. So now we just replace the vector h, which was a vector with n components, by some infinite dimensional object. So instead of depending on an index that goes from 1 to n, now h is going to depend on a position x, where x is in d-dimensional space. And notice that to define a Gaussian probability distribution, it is completely equivalent to specify an action of this form with matrix gamma minus 1, or just the 2-point function, which is given by gamma. And so that's what we are going to do now. We just specify the 2-point function. So we say that we want the 2-point function to be some function g, and g is chosen as the Green's function the Green's function of the Laplacian in d dimensions. And Green's function means the inverse of an operator, of a linear differential operator. Okay, and so in d dimension, this is okay. So in one dimension, this would be proportional to absolute value of x minus x prime. In two dimension, this is log of x minus x prime. And in higher dimensions, this is 1 over distance x minus x prime to the d minus 2. Okay, so this is for d larger than 3, and this is d equal 2. Okay, can you read? Yes. All right, and so this works in any dimension, but we are going to focus mostly on d equals 2. So that case here. And just to fix the conventions, and so let me just fix the conventions. So I will use the following convention. So I will take the Green's function as this. So where x and x prime now are points in R2. And this k here is some positive real number. And okay, so at this point you may say, well, this introducing this parameter is less because I could just rescale the field and then get rid of that normalization factor. But it's going to be important later, and this k will actually be the Luttinger parameter k. So we'll keep it because it will be useful later. Okay, and so now just to complete the definition, one needs to be careful about short range. So we need to have a short range regularization. And this is done by normal ordering. And because you see that if you want to calculate, for instance, any expectation value of, so take some functional of the field H, and let's say you want to calculate its expectation value, then if this function involves the field at the same point, so for instance, imagine you want to calculate some power of H at a point X, then if you use Vix Theorem, then you will see that you will have to evaluate the Green's function at the same point, and this diverges. So it's not well defined, and this is why you need to have a scheme to regularize observables involving powers of H, and this is done by normal ordering. And so that okay, so let me just give the definition. So it can be defined inductively on n. So we can just define H to the power 0. So that's just okay. Normal ordering is written with dots, double dots as usual. So this is just 1. X to the power 1 is just H of x, and then for n larger than 2, we define H to the n of x as the limit when x prime goes to x of H to the this plus k log x minus x prime squared hn minus 2 of x. Okay, so the idea here is simply that you have the plane. This is the plane R2. R2. We have some points x1, x2, x3, x4. We want to calculate the expectation value of h of x1, h of x2, h of x3, and so on. And now imagine that we bring some points together. So imagine that all these points now are sitting at the same position x, and we have n minus 1 of them, and we bring another one, so at position x prime, and we bring it together with the other ones. So when we are going to calculate correlation functions using Vix theorem, then we can pair up all the fields there, and so we have to look at what's going to happen with this one. So there are two possibilities. So this one can either be paired with one of the other ones and not care about those. So this is going to be this is what's going to happen with that term. Or it can pair up with one of these ones, and then as we bring x prime to x, it will diverge. And so we have to cancel that divergence, and this is what's done here. Okay. You may have seen other definitions of normal ordering in other quantum field theory classes, but basically in 2D this is for the free boson in 2D. This is all these definitions are more or less equivalent in the end. So we are going to work with that. And an important consequence of that definition is the following formula. So because we have defined normal ordering, we can now define normal ordered exponentials, which are going to be important operators. And so we can calculate the expectation value of this product here. And the result is this. It's the product of e to the alpha I alpha j of g, which is the Green's function of xi xj. And because the Green's function is given by that above, this is product of 1 xi minus xj to the 2 alpha I alpha j k. Okay, so this is very important. So it's a basic consequence of the definitions, but it's extremely useful in practice. Okay, so in the notes I prepared some exercises, and this is exercise A, so the first exercise. All right, any questions so far? Yes? Yes. Okay. So, well, this is in this exercise. Yeah. So I have absolutely. So I have defined it only for at equal positions, but in practice, if you want to derive this formula, it's useful to define it at different points. And yes. So you have to adapt this. Actually, in the plane, it's okay. You can just define it like that as well for different points. On other surfaces, you have to think a bit more. But, yeah. But for the lectures, I can define it only at equal points. And then in practice, if you want to calculate, you will have to think a bit about the definitions also at unequal points. Okay, yeah, good question. Other questions? All right, so let's move on. Okay, let's erase this. So in practice, one never in physics. It's one usually uses a slightly modified version of this theory, the Gaussian free field, because one has to consider what's called the compactified theory, so compactification. Okay, so let me briefly try to motivate this. So there's one thing that is very useful also in practice. It's that this is very analogous to electrostatics in 2D. Electrostatics in 2D. Because if you have some point-like charges in 2D, then the Coulomb energy, so some charges alpha 1, alpha 2, alpha 3, and so on, then the Coulomb energy is going to be given by a sum of the products of charges times a log. I can put some factor k here, and so then you see that these correlation functions, they're just exponentials of Coulomb energies of distributions of point-like charges. And now there's something quite important, which is that there's a duality in electrostatics. Let me erase this. Okay, so what does an electric charge do? So an electric charge creates a potential, and then you can define an electric field as the minus the gradient of that potential. And so if you look at the lines of that electric field, if you have an electric charge here, you have lines that are going there. Okay? So that yeah, and the electric field is a solution to the to Gauss's law, and let me just try to get the coefficients right. So yeah, so the electric field is a solution of this. So the alpha j's are the electric charges. Okay, so this is Gauss's law. There's another law, which is Faraday's law, which is that the rotational of E has to vanish. Okay, so the electric field is a solution to these two equations. But now you can imagine that we have another type of configuration with a small solenoid going through the plane like this, with a magnetic flux that increases, such that in the presence of a charge of a magnetic charge here, the equations would become instead this. So now Gauss's law reads like that because there's no electric charge anymore, and there's a magnetic charge, so that Faraday's law becomes this, with some magnetic charge beta j. And so in the presence of a magnetic charge, then the lines of the electric field are going to look like this. So they're going to turn around. Okay, and now you see that the two kind of charges are dual to each other, because if you so if you, what can I erase now? This. Yeah, so if you do the following transformation, so you map the electric charges and magnetic charges to, so you exchange them up to a sign, and you exchange the two components of the field. So E1 and E2 are the two components of the vector E. You change that to 1 over 2k E2 minus E1, and you change also k to 1 over 4k. Then you see that basically you're back at the same situation where you have exchange old electric and magnetic charges. So what this duality transformation here does is that it rotates the vector E by pi over 2, so clockwise. And so if I take the vector E here, which is pointing like that, and I rotate it by pi over 2 clockwise, then it points like that. And so if I follow the lines of the new E, I see that they are turning around like this. So it looks like this. And if I do the same here, take this vector here, rotated by pi over 2, I see that now the lines are going like that, but they're going inwards, except of instead of going out, they're now going in, which is reflected by the in the fact that this charge has changed sign here. Okay, so this is basically electric-magnetic duality in 2D. And so we have seen that this the correlation functions of this Gaussian free field, of these exponentials of the Gaussian free field, are given by something that is analogous, something that is the exponential of the Coulomb energy of a set of electric charges. And so we can ask, is there an analog of magnetic charges? And the answer is yes. And this happens when we make the field compact, which is what I'm going to explain now. So what does it mean to make the field compact? Okay, so that's right here. Yeah, so what's this supposed to be? Okay, so compactification, compact H. So so earlier H was just so H of X was just a function. So H is a function from R2 to, so it's a random function. It's a distribution of functions, but on functions that go from R2 to R. Just take any real values. And now we want to make it compact by changing the target space here. So we replace R bar R modulo 2 pi. So that means that H now has to be identified with H plus 2 pi. So I'm not going to explain why this. I'm not going to explain why we do this. You have to look at microscopic models and think of this Gaussian free field as an effective theory describing long-range correlations. And then if you do that properly, then in many microscopic models, then you actually see that this is the right way to think about it. So I'm not going to explain this today because I don't want to enter any details of microscopic models. So let's just take this for granted and see what the consequence of this is. So there are two consequences. Let's erase this. So there are two consequences. So if we have an observable, the first consequence, first consequence. So if we have an observable f, so some function that depends of h as a point x, properly normal ordered, then now that we have imposed this, so this is now well defined only if this is invariant under addition of 2 pi. And so this means that f has to be a periodic function of h. And since it has to be a periodic function of h, I can always write it as a Fourier series with some coefficients of e to the I p h of x. And those exponentials now are normal ordered. So that means that any local observable of that form now has to be a sum of these exponentials. And these exponentials I'm going to call, so these are usually called the vertex operators, and okay, so we are going to write them as v, p, 0 at position x. So the p refers to this p here, and the 0, so this is the analog of the electric charge, if you want, this p. It's this alpha here up to a multiplication by I. And the 0 here will be the magnetic charge, which is 0 for this operator. But we'll see that there are other operators for which the magnetic charge is not 0. So that's the first consequence. The second consequence is that there are new local operators in the theory. Because, so again, let me write here. Because if you view now h as a function from R2 to the circle, so R quotient, real numbers modulo 2 pi. So this is a function from the plane to the circle. So at each point here, you associate a point on the circle. But now if you imagine that this is point x, so this is a point x, which maps to the circle. This is h of x. So now if you imagine that we have that you have punctures, for instance, a puncture at some point y here, and so y1, y2, so you are working in the plane with punctures now. So now we have a function from the plane with punctures. Y2, y3. So now this is not simply connected anymore, and so when you turn around one of the punctures, so for instance if this point turns around here, then the value of h can also wind around the circle, and so there's a certain winding, integer winding that is allowed, which you can. So if you follow h around one of the punctures, cy, let's call it. Then, okay, this has to be 2 pi times some integer, where q is an integer. Okay, 2 pi because h is defined modulo 2 pi. And so we see that there's a second type of local operators in the theory now, and the second type of operator is the operator that creates a puncture at a point and imposes that winding on the field H. And so these are the magnetic operators. And those operators I'm going to write as V0Q at position Y or X. Okay, so we have seen two types of operators. Those are the magnetic operators by analogy with electrostatics. We have the electric operators also by analogy with electrostatics, and we can also bring them to the same point, and then more generally we have operators that have an electric charge and a magnetic charge, which look like that. Okay. All right. Yes. So H, okay. So the Gaussian free field is a random distribution on functions H, and the functions H are functions. These are the fields. It's the field in the theory, and the field is a map from a base space, which is a two-dimensional plane, to a target space, which in this case is a circle. Yes, another way to say this is that this is like a random surface, because so you take the plane, any point in the plane is mapped to okay, so let's do the non-compact case, and then any point on the plane is mapped to a real line. But then this, you can view this as a height, as a certain height. And then this is like defining a random surface in 2D. So this is like looking at all the set of points x1, x2, and h of x1, x2. Two components of x and h of x in 3D. Okay, so that's a random surface. Yes? Yes, thanks. Yes, exactly. That's yes, thank you. So yes, this is valid. Right. Okay. So this here is valid when you put it in when you calculate this. So you insert a bunch of these magnetic operators at positions x1. Xn, yes. So you calculate this. You may want to normalize it by dividing by this correlation function. So you have to look at this correlation function as a correlation function where you have changed the allowed configurations in your path integral. Yes, exactly. So this here is valid when you look at this object. This is now a function of x, and if I calculate this integral along the contour around a point xj, then I will find 2 pi qj. Yes. Sorry, which one? What? Because so if I write the same identity here for electric operators instead, yes, exactly. You will see that it satisfies. Okay, so not this equation, but it will satisfy. Yeah, let's do it. So if I write, so the okay, so here I put now some electric operators. Let's put just one for simplicity. So then if I calculate this, so divergence of this, so this is the Laplacian of H, I will find that it's this is at position x1. I will find that this is 4 pi times delta 4 pi k times delta x minus x1. So this is like a Gauss law, analogous to Gauss law, and there's an I here, which is important. Yeah. So it's like Gauss law with imaginary electric charges. Sorry? P, yes, P, sure, yes, P1, yeah. Yes. Mm-hmm. Sorry? Yes, so that's what comes next, yes. Mm-hmm. 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 No, so that's what comes next. Yes. Okay. All right. So yes. So how do we represent it in terms of local fields, and how do we calculate correlation functions of these operators? So let me keep that, because this is going to be important. Yeah, so there's a trick. There's a trick which is generally valid in conformal field theory, which takes a particularly simple form in this boson CFT, or Gaussian free field, which is that you can basically local observable tend to factorize into a left moving part and a right moving part. And what this means here is that H at position X. So now let me switch to complex coordinates. So I will write. So don't be afraid by complex coordinates. They really don't mean it's really no different from coordinates x1 and x2. It's just that it's more convenient to write formulas. So okay, so H at the point x, which I will now write as z bar. Can formally be written as this. This is important. Where phi and phi bar are again Gaussian random fields, if you want. So they also satisfy Vix theorem separately. And now the 2-point function of phi is defined as this. And the 2-point function of phi bar is defined as that. So the cross well, so the correlation functions that involve phi and phi bar are 0 in the plane. This will change later, but in the plane it's 0. Okay, so you can check easily that this is compatible with the formula I had earlier for the 2-point function of h. You just calculate the 2-point function of h out of this definition here, and you will see that it all works fine. And now using this chiral, this decomposition as a chiral and anti-chiral field, it's very easy to write both electric operators and magnetic operators, because so the electric operators, as we've seen, are simply defined as these exponentials. So then if I write it, I write the exponential in terms of phi and phi bar. This simply becomes e to the I p root k phi, e to the I p root k phi bar. And turns out for the magnetic operators you can also find a form like that. It's just that you have to change one of the signs. So this becomes e to the iq over 2 root k phi of z, e to the iq over 2 root k phi bar of z bar. And you can check using Vix theorem that if you calculate this expectation value here, it will have the correct winding. So maybe I can write that. Yes. So actually, okay. So if you calculate this here using that definition here, you will actually okay. So let me erase that. I calculate this expectation value, properly normalized. So when I normalize this, it just actually kills all the terms in Vix theorem that would come from contracting those operators. So the only thing I end up with is contractions of this one with one of the other ones. And so then the result is that when I calculate this is just sum or a qj of the argument of z minus zj, and the argument with the minus sign, and the argument here is just winds by 2 pi as it should. So it is by construction it has all the correct windings. Now, yes. What formula? This one? Well, I mean, compactification is just a convenient way of thinking about allowing such operators, right? If you don't have compactification, then what does it mean to just have h jump by 2 pi? I mean, you can define whatever you want. It's just talking about compactification somehow makes the whole thing more consistent. Because then in this compactified language, all these things are local operators. If you were not compactifying, then you would have to talk about non-local operators. All right. Now, yes. So using this chiral representation, you can actually evaluate this correlation function. Let me write it here. So it's again an exercise in Vix theorem, which you can do, and you find the following. So this is equal to product of zi minus zj. Let me just write this, otherwise we'll get it wrong. Qi qj over 4k. And okay, so notice that it's basically the same formula as here, except that k has been changed to 1 over 4k, so this is this duality here, which is not surprising because we have switched electric and magnetic operators. Okay? Yes? Well, I just I replace h by this, and I replace v by the corresponding expression in terms of the phi's, and then I calculate with the phi's using Vix Theorem for the phi's, and I find this result. Yeah, and I just use those two propagators here. Yeah, so okay, so what's important here is notice that this is the same correlation function as this one, basically, up to the fact that we have switched k by 4k. And also here, notice that alphas were real, and now as I said, we have to work with alpha equals I times an integer, IP. And so if you put alpha equals IP here, then this thing goes in the numerator, not in the denominator, and so it really looks like that. Okay? All right, so this is correlation functions. Basically, this gives you all correlation functions you want in the plane. You can easily generalize these expressions to correlators where you have P and Q that are non-zero. Just that it gets a bit more messy, and so I don't want to write them on the board, but they're in the notes. Now, how much time do I have? 0. Well, this is maybe a good place to stop then. Yes. Yes. Okay. So I have to go a little bit faster. So I just wanted to very quickly say something about bosonization. So I will not go very far. So okay, so first, we've discussed the free boson CFT or Gaussian free field, but there's another free theory which is extremely useful in condensed matter applications, which is the free Dirac theory. And this is defined as follows. So it's a Fermion theory now. So you should think of this, it has 4 fields. You should think of these fields as being Grassmann variables, so they anti-commute. So the bars are for anti-holomorphic dependence. These are holomorphic, and the dagger is for charge conjugation. So these things have a charge. And so it's defined as the theory that has these propagators, or 2-point functions. So this is 1 over z minus z prime, and this is z 1 over z bar minus z bar prime. All the other 2-point functions are 0. And then these objects satisfy Vix theorem for fermions. So Vix theorem for fermions is the same as the one for bosons, except that we have to be careful about the minus ones that show up when we commute the fields. So for instance, if we look at the 4-point function, let me write it like that. So there are two ways of pairing these fermions so that we pick up 2-point functions of that form. So the first one is if I pair up this one. Okay, let me call. Okay, so if I pair up the first one with the last one, the second one is if I pair up the first one with the third one and the second one with the fourth one. So here I have a crossing, and because I have this crossing, I need to put a minus sign. So now this becomes 1 over z1 minus z2. z1 minus z1 prime, z2 minus z2 prime, minus, this minus is extremely important, minus 1 over z1 minus z2, z1 minus 2 prime, z2 minus z1 prime. Okay? And okay, so that defines the theory. It allows to calculate any correlation function. You can define it as a path integral also if you prefer, but it's completely equivalent in the end. So this is the theory, and okay, so the important formula in that theory is that the general endpoint function for the fermions, for the chiral fields, is given by that. Okay, so let me put n of them. Okay, so you write it with Vix theorem, you pay attention to the minus signs, and then you will see that this turns out to be a sum over all the 2-point terms, so psi zi dagger zj, with some minus signs, and the minus signs, okay, so it's a sum over permutations over permutations of the n elements with a signature, where sigma is a permutation, and you pick up the minus 1. So the signature of the permutation is and z prime of sigma of j. Okay, so this is by definition the determinant of that matrix. So it's the determinant of the 1 over zi minus zj prime for I, for the matrix, for that matrix. So this is the general 2-endpoint function of the Fermion fields in this free Dirac theory. And now, sorry? Right, yes, product of, yeah, I guess all the pairs I and j. Yeah. Thanks. Yes. So this is the important formula, and now you can ask whether this this theory you can represent in terms of bosons, and the answer is yes. There's one thing you need to do compared to what we have done so far. So far, I've looked at this free boson theory, or GFF, with a certain parameter coupling constant k. And I discussed what the local operators were in this theory, and I said that the local operators were all of the form VPQ of Z z bar, and also there are two other ones which are okay. The derivatives of h are also local, but we won't pay attention to those, so let's forget them. So these essentially are the only interesting local operators, and non-trivial local operators. And so we can ask whether these fermions we can represent in terms of bosons. But fermions are not local, have non-integer spin. Sorry. No. So the fermions are non-local, so we can't represent non-local operators in terms of local ones. So we have to allow for something. And this something is that we need to allow for observables that are not invariant under the shift h goes to h plus 2 pi, but only invariant up to a sign. So instead of having these operators of this form, where p is an integer, I will now allow p to be half integer, and then this thing will be defined only up to a sign, and this is basically what fermions are also, observables that are defined only up to a sign. So by allowing p to be half integer, then you can indeed represent fermions in your theory, in your bosonic theory. And in fact, you can check that if you look at the four operators v 1/2 1, v 1/2 minus 1, v minus 1/2 1, and v minus 1/2 minus 1, then in fact these have the correct. Okay, so you want to identify those with psi dagger with the four fields in the fermionic theory. And in order to be able to do this, they need to have the correct quantum number. So they need to have the correct charge, the correct spin, and the correct dimension. And so if you just write it down, you will see that this works only if k equals 1. So this is quite important. Free fermions map to a free boson theory with Luttinger liquid parameter which is equal to 1. And okay, so if you take k equals 1 and you write what these operators are in terms of the chiral fields phi and phi bar, actually you will see that they are of the form. Okay, so I'm not gonna try to write it exactly because I'm gonna mess up the signs, but they're of the form e to the I phi of z, e to the minus I phi of z, and same thing for phi bar. So there are 4 of them in total, and these you identify with the 4 fermion fields. So notice that they are chiral. These are chiral. So somehow by taking 1/2 and 1, or here, you have you got rid of the anti-chiral dependence. Similarly, the other ones are anti-chiral. So this is consistent with the fact that we can identify them with the fermions. And now this has a non-trivial consequence, which I would briefly like to discuss. So once we have identified these, so basically this I want to identify it with the field psi, and this I want to identify it with the field psi dagger. So now this has a consequence, because you see this correlation function I can now evaluate using Vix theorem for bosons. So I can use the formulas that we've found so far using for these correlation functions of exponentials of the field h or the field phi, which works in the same way. And so if I do this identification, then this correlation function on top there Okay, let me just write it like this. Okay, so this the same correlation functions as the one on top here now becomes this. Okay, so this is C1 prime. It becomes a correlation function of these normal ordered exponentials. And if you calculate this using what we've done before, so using Vix theorem for bosons, then you will find this. Okay, so this is for okay, so it's the same kind of products of so it's an exponential of a bunch of Green's function. And since the Green's function is a log, and you take the exponential, it gives these products. So this is what you find if you do the calculation in the bosonic language. So notice that this is not the same formula as this one. Okay, so the question is, are those the same or not? If they are the same, then somehow this identification of bosons and fermions is okay. If they're not the same, then it's just wrong. So, okay, so does anybody know what this is? Yeah, I heard it. Who said it? Yeah, say it aloud. Yeah, it's called the Cauchy determinant formula. So basically, that's what bosonization is in the language of correlation functions. It's, I mean, of course, there are other ways to discuss bosonization, but at the level of correlation functions, this identification between fermions and these exponentials of bosonic fields with k equals 1, again, this is important. It boils down to the Cauchy determinant formula. So this allows to view bosons as fermions and fermions as bosons as long as they have the correct coupling constant. So what states are you talking about? Hmm? Right now we have operated everything in one state, right? And then, so in the equivalent space we have more states with other functions, right? So other Gaussian states. So this identification we also provided for other Gaussian states. Well, I didn't talk about states, right? So I'm not sure I want to enter that discussion. Yes, exactly. I took as a definition. So you want to change the definition, but I'm not sure I want to do that. I mean, yeah, you can do all sorts of things, but. My question is like whether this already shows that we can represent fermions and bosons and identify the whole Hilbert space, because now we are looking for the agreement of the ground. Yeah, so you want to discuss bosonization in the language of states, and okay, checking that one Hilbert space is the same as the other, but I just don't want to do that. So. Yes, I mean it's in the end it's all equivalent, but yeah, sure, yeah. So there are various ways to look at the field theory. You can discuss field theory in operator language I thought for this lecture, I just thought it was easier to focus on just correlation functions. So define a field theory as a set of correlation functions, and this is so in that context, this is how I thought bosonization should be discussed. But of course, there are other ways to discuss it. In the end, everything matches, right? Okay, thanks. So, okay, so now, all right, so now I need to go to surfaces with, so far I discussed the correlation functions only in the plane, but it will be useful next week, and more generally in condensed matter applications. It's usually important to consider also surfaces with boundaries, and the archetype of surfaces with boundaries is the upper half plane. So upper half plane. So what's the upper half plane? Well, so you know what the plane is. So this is R2, and now this is the upper half plane. So I just okay. So this is the real axis here, right? So x, y. This is x, y, and this I will call H. Okay, so it's the set of points in C, such that the imaginary part of Z is larger than 0. Well, okay, this is H. Okay, so to define the Gaussian free field in that in the upper half plane instead of the plane, we have to. So I want to use the same kind of definition as what I said earlier. So I just want to define it in terms of a certain Green's function. But then we have to construct the Green's function for the Laplace operator in the upper half plane instead of the one in the plane. Okay, so recall that the Green's function in the plane was, we defined it as yeah, okay, let me write it in complex coordinates. So we defined it as this. So it depends on the 2 points x and x prime. Because I'm writing things in complex coordinates now, I have 4 of them. This is just a notation. It's not a new dependence on anything. It's just to remind us that this is neither holomorphic nor anti-holomorphic. And so this is minus k of log z minus z prime squared. Okay, so this is what we had so far. This was in the plane. So this is the Green's function of the Laplace operator in the plane. And now I want to modify this slightly such that I have a Green's function on the upper half plane. So to do that, I need to specify what kind of boundary condition I want to satisfy along the real axis, which is the boundary of the domain. And so there are the two most important boundary conditions for applications are Dirichlet and Neumann. So Dirichlet is defined. So if I have my field H, so my function H on the upper half planes, then Dirichlet would be H equals 0 along the boundary, and Neumann is that the perpendicular derivative, so the component of the gradient that is perpendicular to the axis. So okay, so that's the derivative along y in coordinates x, y. That this is 0 also along the boundary. So now, since I want to identify the 2-point function h of z bar h of z prime bar with that Green's function here, to find a Green's function that satisfies these boundary conditions. So two different Green's function, one for Dirichlet and one for Neumann boundary conditions. And so this is actually an extremely well-known problem. And the way to do this is to use the so-called method of images. Which is a very standard thing to deal with boundaries, either in harmonic analysis or in electrostatics, or basically all fields which have to do with looking at the Laplacian. So the method of images is the following. So we think of this Green's function G as being the electrostatic potential created at position Z by a point-like charge at position Z prime. This is basically what it is. It's a logarithm of the distance. And then we just say, now if we have a boundary, so now let's put this in a domain with a boundary, and let's imagine that the boundary is like a perfect conductor, then or some other standard boundary condition that you would consider in electrostatics, then the thing to do is to say that the electric field that is now felt at this point, or the electrostatic potential felt at this point, is going to be, let me just move this one a bit, is going to be the sum of two contributions. So the sum of the potential created here and the potential created by a mirror image. So this is now in complex coordinates z bar, because I just put a minus sign to the imaginary part. And so now this point here fills the potential created at this point and also the potential created at this point. And I just need to adjust the charge of this guy here so that I pick up the correct boundary condition. So, okay, so let me give you the result. So for Dirichlet, this now becomes this with a plus sign here. And for Neumann, it's the same, but with a minus sign. Okay, so for Dirichlet, it's clear that this has Dirichlet boundary conditions, because if z is along the real axis, so z is real, then this is the complex conjugate of that, so they have the same modulus, and so the two terms cancel, and this is 0. For Neumann, it's also clear that you just need to, I mean, maybe you have to write a one-line calculation, but it's easy. So these are the Dirichlet and Neumann boundary conditions in the upper half plane, and this allows then to define. So everything we've said so far, it goes through to the upper half plane, with either with Dirichlet or Neumann boundary conditions. And from now on, I will focus only on Dirichlet, because these are this is the Dirichlet boundary condition that this is the boundary condition that we are going to need mostly next week. But in fact, we will see that because of duality, the Neumann boundary condition is never really far, even if we are working with Dirichlet. So yeah, maybe just let me point that out. So under this duality, so this electric magnetic duality, which I said was taking the field E and rotating it locally by pi over 2, such that it transforms electric charges into magnetic charges. Well, so you see that it exchanges Dirichlet, the duality exchanges Dirichlet and Neumann boundary conditions, simply because it exchanges the normal and parallel components of H along the axis. And so if you have Neumann boundary conditions, so that this is 0 along the axis, then under duality it becomes a Dirichlet boundary condition, and vice versa. So in the other way around, you have to fix a gauge somehow, because if this is 0, it just tells you that, well, this way actually. If this is 0, it just tells you that H is constant along the boundary, but then you can just fix it to 0 without loss of generality. So under duality, Dirichlet and Neumann are exchanged. So this is the duality that we've talked about earlier, so which exchanges k and 1 or 4k. Okay, so now with Dirichlet boundary conditions, I want to be able to calculate correlation functions of these operators that we've talked about earlier. These V, PQ, and again to avoid formulas that become increasingly ugly, let me just focus on the case where there's either electric or magnetic, but not both at the same point. So now imagine I want to calculate a correlation function like that in the upper half plane. In the upper half plane. This is most easily done by using again this Chiral factorization that I presented earlier. So we can just represent H as root k times phi plus phi bar. Well, this is holomorphic, this is anti-holomorphic. So we do that. This is now I root k p1 phi plus phi bar. Phi 1, phi, okay, let me. E to the I root k pn phi n plus phi bar n. And now we have to use the boundary condition. Because of course the result is not going to be independent of the boundary condition. The boundary condition changes the physics, so the boundary changes the physics, and it depends on the boundary condition that we are imposing. So at some point we need some input from the boundary condition. The boundary condition here is that H equals 0 along the boundary, and so we see that phi of z equals minus phi bar of z bar if z bar is if z bar is along the boundary, so if z is real. Okay. And so this actually a convenient way of looking at this constraint is to say that phi bar. So both fields are defined in the upper half plane, although so both fields are in principle defined in the upper half plane. So this is H. So both fields are living here. So some field phi, some field phi bar. But now it's convenient to imagine that phi bar is actually the analytic continuation of phi, or minus phi, because of this minus sign here, to the lower half plane. So yeah. So in other words, phi bar at z bar, we are now going to identify with phi of minus phi of z bar. And we are going to say that phi is just analytic everywhere in the whole holomorphic everywhere in the entire plane. So this is like the method. This is again an occurrence of the method of images. It's just expressed in a chiral way somehow. And this is very general in conformal field theory. This is how you deal with conformal field theory with boundaries. And so, okay, so now we just impose that phi equals minus phi bar at position z bar. And so then this gives us, we can do this substitution here. This gives us phi 1 minus, okay, phi 1 at position z1, phi at position z1 minus phi at position z1 bar. And so on, same thing for all the operators. And then this can be calculated again using just the 2-point function of phi, which was just minus log of z minus z prime. And so the result here is okay. So it's product of I smaller than j of z zi minus zj k pi pj. So this is going to be absolute value squared times okay, sorry, let me yes, okay, times product of element minus PLPM times K. Okay, so this is again the same type of formula as earlier. It's the exponential of some sums of logarithms. So it's always the same thing. And what I would like simply to emphasize is the following. So that it's that this result here you can rewrite as okay. So the correlator of these electric operators we can rewrite as the exponential of minus sum of PL squared over 2 G, okay, G. So this is the Green's function with Dirichlet boundary conditions. Yes, okay, so this is the Green's function with Dirichlet boundary condition that we've defined here. And this object here, which depends on a single position, now is the, okay, so it's called the regularized Green's function. And it's just defined as, it's kind of the same definition as normal ordering, it's just it's defined as okay, so for a point x, it's defined as the limit where x prime, when x prime goes to x, of this plus k x minus x prime squared. So this diverges when x prime goes to x, but if you remove the divergence, it gives you some finite result, and it pops up in the correlation function. The interpretation of this here, again, is that this thing you can interpret as the Coulomb energy of a distribution of electric charges. This time in the half plane instead of being in the plane. So what happens is that you have the upper half plane here. You have a bunch of electric charges, and all the charges interact with each other. They create, this one creates a potential which feels the boundary, which depends on the boundary, and this one feels the potential created by this charge in the presence of the boundary. This is what is expressed by this term here. And on top of that, each charge feels the interaction with itself because of the boundary. So that would not be here in the full plane, but because there is a boundary, if you have a single charge, it has a non-zero energy because of its interaction with the boundary. This is what you see here. Now, this is the correlator of electric charges again. By duality, you can just write down the one for magnetic charges, which is what we are going to need next week. Okay, so maybe just to not to waste time, I will not write it. So okay, so basically you can just replace the p's by q's here. And if you just change, this is the Dirichlet, the Green's function with Dirichlet boundary condition with a coupling constant k. If you change k to 1 over 4k, you exchange Dirichlet with Neumann and so on, then you get the result. Okay, so I will not go through it. And instead, let me finally arrive at perhaps the most interesting part, which is conformal invariance. So far I discussed only the plane and the upper half plane. But the point is that once you have those two surfaces, then you can really do a lot. And that's thanks to conformal invariance. So what is conformal invariance? So a conformal map from one surface equipped to a metric to another. So from one surface M with some metric G to some other surface M prime with or manifold with some metric G prime. This is true. This is a definition that holds in any dimension. So it's just it's a map that preserves the angles, which preserves the angles. And now, in 2 dimensions, this is particularly interesting, because in 2 dimensions, so if you have in 2 dimensions, you can see that there's that this has to do with a complex analysis, because if you imagine that if you choose some local coordinates such that the metric takes the form. So this metric here takes this form. So this is just a coefficient, and so it locally looks like a Euclidean metric times a coefficient. You do the same for the other one here. So so we use coordinates z bar for this one, and let's say we use coordinates w bar for the other one. So the metric of this one is 2g w bar. dw bar. So if it's in 2 dimensions, if it's a transformation that preserves the angles, then it has to look locally at least like a rotation times a scale transformation. So that means let's imagine that our map that sends z bar to w bar that it sends 0 to 0, just without loss of generality. You can just pick the coordinates such that this is true. And then locally around 0, in order for this to preserve the angle, if it is to be locally a rotation, then we see that this w, which depends on z and z now, should look like a rotation, so some angle, so some phase, e to the I theta times z, times a scaling transformation, so times some coefficient lambda, and lambda has to be positive. So locally, this is the most general thing that can happen, and because of that, you see that w depends only on z and doesn't depend on z bar. So in 2D, conformal maps are exactly the holomorphic functions whose derivative doesn't vanish, because you want dz bar of w to be 0. That means it's holomorphic, but you want dz of w to be non-zero, because otherwise this is not locally conformal. Okay, so this is conformal invariance in 2D, and this tells you that basically any holomorphic function is going to provide you with a nice conformal map. Okay, so I have 5 minutes left. Yes. Well, it's local, but then it's true everywhere. Yes, so it has a singular point where this is not going to be 0, and then yeah, it's not 1-to-1. So okay, so some people add the condition that it should be bijective in the definition. So they call conformal maps only really bijections from one surface to another. You don't necessarily have to do that, but for what I'm going to say, okay, I'm going to give actually only 2 examples, and the 2 examples are going to be bijections. Yes. Okay, so the most important example which we will need and which is really useful for many applications is the map from the infinite strip to the upper half plane. So the infinite strip is just this domain, so it's so we have coordinates x and y. Z is x plus iy, and so x, the point x, y is in the interval 0, L. This is x equals 0, x equals L times R. So this is a certain domain, and it can be conformally mapped to the upper half plane. So okay, let me draw it like that. Can be okay. So if I draw lines like this, then this is conformally mapped. It sends those lines here. And this is the upper half plane, and it's so this. If I have a point W here and a point Z here, the map that sends Z to W is, so Z is sent to W of Z, and this is exponential I pi Z over L. So you can easily check that this here does what I say. Notice that it's holomorphic, as it should. So this is actually, yeah, so this is, I mean, it's kind of trivial, or not complicated, but it's extremely useful in practice. Now there's a more conceptual result, which is good to know, which is Riemann mapping, the Riemann mapping theorem. So there are many existence theorems about conformal maps. Perhaps one of the most important ones is the Riemann mapping theorem. And so the Riemann mapping theorem tells you that if you have some domain, some subset of the complex plane, which is non-empty, simply connected, and not C itself. So you can think about what this is, but basically it has to be of this form. So it has to be either a compact surface like this, which is subdomain of C, or something that goes to infinity at somewhere. But so the theorem tells. So in particular, the infinite strip is one domain that satisfies these assumptions. And what the Riemann mapping theorem tells you is that there exists a conformal map. So if I use complex coordinates here, there exists some conformal map that sends this to the upper half plane. So again, some map that sends Z to W. So there exists a conformal map, which is a bijection. Exists so a conformal map sending U to the upper half plane. Okay, so this is more conceptual than just this example. In practice, the theorem, of course, doesn't tell you how to construct the map, but there are also techniques to do that, at least in an approximate sense. So basically, I'm finished. There's one extremely important thing that I need to say, and then we are done. So what does conformal invariance have to do with the Gaussian free field, and more generally with field theories in 2 dimensions? So for the Gaussian free field, it's because the Gaussian free field is invariant in the following way. So of course, if you have a domain, let's take one of these domains that satisfies the assumptions of the Riemann mapping theorem, then we need to just to define the Gaussian free field, we need to cook up a Green's function in that domain. Let's say with Dirichlet boundary conditions again. But then this is very easy because we can use the fact this is very easy provided that we have a map to the upper half plane. Because if we have a map to the upper half plane, then we can just choose. So this is a map Z to W. So then we can just choose the Green's function with Dirichlet boundary conditions as minus k times log of W of Z minus W of Z prime divided by W of Z minus W bar of Z bar. Okay, the whole thing bar here. Okay, so what does this identity means? It just means that first you use the mapping to go to the upper half plane, then you use the method of images, and you're done. So then so this provides us with a Green's function. So it defines the Gaussian free field on this. So it defines the free boson CFT on any surface of this kind. And now the last thing is that since we are interested in calculating correlation functions, the important thing is that correlation functions behave in a special way under conformal mappings, and this allows to write correlation functions on any surface using this kind of tricks. And the special way in which correlation functions transform is as this. So if you have a so-called primary operator, so the primary operators are so primary operator, let's call it phi. So a primary operator is an operator that transforms as follows under a conformal map. Where H and HR are the so-called dimensions, so they're related to the. Let's keep it like that. So they transform as this. So notice that if you have an operator that transforms as this, then its derivatives will not transform as this. So will not transform in the same way. Transform in the same way. So there's only a certain kind of local operators that transform in that way, and they're the most local ones in the theory, if you want, because all the other ones. So one of the postulates of the theory is that either an operator transforms in that way, and then in that case it's one of the primary operators, or it does not transform in that way, and then it can be obtained as a combination of derivatives of those. And now in the Gaussian free field, the primary operators are precisely the VPQ that I have defined. And so the VPQ transform in that way, and then you can use this to write correlation functions of these operators, which is what we are going to need, which is what is typically needed in Luttinger liquid theory. Well, you can use this machinery to just write down correlation functions on any surface without having to calculate much, basically. Okay, so that's it. Thanks.